As we discussed for delta S naught for the universe, or the change in entropy of the universe, many reactions are product favored at some temperatures and reactant favored at others. This occurs when one of the terms in the Gibbs free energy equation is favorable and the other is unfavorable. We're now going to look in more detail at these types of reactions to understand why this is. Let's take the example of the freezing of water at 1 atmosphere. That's when water as a liquid turns into water as a solid. Now delta H fusion will be negative because energy is released as the bonds are formed. Delta S is also negative. The disorder decreases as the crystal forms. You went from a solid to a liquid. So we have our Gibbs free energy here. At what temperatures will this reaction be thermodynamically favorable? To be thermodynamically favorable, delta G has to be negative. That's how we defined it. So the phase change will occur at low temperatures. The reason for that is the term negative T delta S has a positive value, and this is minimized at low temperatures. Let's look at the combustion of gasoline, which is the C8H18, or another name for that is octane, and it's combustion because you're burning it with oxygen, at 1 atmosphere. Delta H is negative because energy is released as new bonds are formed. And delta S, the change in entropy, will be positive because you've increased the number of moles of gas products. That doesn't always work, but in this case it does. And here we have 2 moles of gas plus 25, so that's 27. Your products, there's 16 plus 18, that's 34. So that's an indicator that entropy goes up. At what temperatures will this reaction be thermodynamically favorable? Well, let's look at our Gibbs free energy. Delta H is always negative, okay? Negative T delta S, well, what's that? Delta S is positive, so negative times a positive will be negative. So I have 2 negative numbers here. You add them together, we're going to get a negative value for Gibbs free energy, so the reaction is favorable no matter what the temperature is. Example number 3, photosynthesis, basis for life on Earth here, right? Carbon dioxide plus water yields oxygen and sugars. Delta H is positive since energy is absorbed to create new bonds. Change in entropy will be negative since many moles of gas are converted to fewer moles of gas. Well, let's just check that. We have 6 plus 6, that's 12. And on the right side, we just have 6 moles of gas. So at what temperatures will this reaction be thermodynamically favorable? We'll take a second before I move the answer, so you can pause the video if you'd like. And now we're going to move the answer away, or the cover of the answer. And what do we see? The reaction is unfavorable at all temperatures, as both the enthalpy and the entropy terms are positive. So what do we mean by that? Well, delta H over here, that's positive. Now we said delta S is negative, okay, but we're multiplying it by negative T, negative times a negative, positive. So that's what we mean. There's your enthalpy term, here's your entropy term. Plants need energy from the sun to grow. A continuous input of energy is needed for this reaction to occur. Plants won't grow in the dark. Final example for this. Dissolve ammonium chloride in water. Delta H is positive because the energy is absorbed to break existing ionic bonds, and delta S is also positive. There is an increase in disorder as ions mix with the water. So we have our Gibbs free energy here. At what temperatures will this reaction be thermodynamically favorable? So what do we have? This one's a little tricky. The reaction is favorable only at relatively high temperatures, right here. When the negative term, negative T delta S, is greater than the positive delta H term, then we will have a thermodynamically favorable condition. So we need a big value of T, high temperatures.
All right, so in this slide, we're just going to walk through what are the signs of delta G 0 for the system, for each of the possible scenarios, or for each of the possible signs for the enthalpy and the entropy. Okay, so if the delta H change is positive and the delta S is negative, okay, what does that do to the equation? Well, the first term here would be positive. And then you have minus. Then this delta S term will make this whole thing negative. So minus multiplied by this negative gives you a positive term there. Okay? And so what that results in is this delta G will always be positive because we're just adding together two positive numbers. So you can see that right here, that if delta H is positive and delta S is negative, for all temperatures, delta G is always positive. Okay, now, what about the second scenario? The one in which, so we did this one already. What about the scenario in which delta H is positive and delta S is positive? What happens there? Well, the first term, the delta H term, is positive. Then we have minus a T delta S term, which is also positive. So a positive number minus a positive number. So it depends on how big the number is that you're subtracting, right? If this number here is small, then the overall difference will be positive. The larger that term gets, the more likely or the possibility of delta G being negative. Well, how do we get a low positive term there? The only way to do it is the temperature. So the lower the temperature, okay, so if the temperature term there is small enough such that that second term is less than the first, then delta G will be greater than 0. Okay. The bigger this temperature gets, as this temperature climbs and climbs and climbs, then this second term here gets bigger and bigger and bigger. And if you're subtracting a more positive number, then you get a difference that is negative. So the greater the temperature there, delta G is less than 0 or negative. So that's what we see here. For high temperatures, delta G is negative, and for low temperatures, delta G is positive. Okay, now what about the third scenario where we have delta H is negative and delta S is negative? So we have a negative term minus, now again we have minus a negative term, which means plus a positive. So a negative number plus a positive number. All right, so there's a couple of things here. If that positive number is greater than the negative number, then delta G ends up positive. How do we get a second term here that's positive greater than the negative? Well, again, we increase the temperature. So the greater the temperature, the more positive the difference will be, or delta G will be greater than 0. And the smaller the temperature, then this negative term here will be larger in the difference. And so the smaller the temperature, delta G will be less than 0. Okay, so that's what we see here. At high temperatures, delta G is greater than 0, and at low temperatures, delta G is less than 0. And then our final possibility, if delta H is negative, right, an exothermic process, and delta S is positive, right, increasing the entropy of the system. Those are both favorable things, right? If we have an exothermic process and we're increasing the entropy, we would expect that to be spontaneous, right? But the math also shows us that that's true. Okay, let's look at our last scenario here, where we have delta H is negative. That's an exothermic process, right? And delta S is positive, one in which the entropy is increasing. Both of those things we would expect would lead to a spontaneous process, but we could show it here with the math. So we have a negative minus a positive. So keep in mind that subtracting a positive number is the same as adding a negative number mathematically, right? So we're just adding two negative numbers together. And if we're just adding two negative numbers together, then our difference is just going to continue to get more and more negative. So in this case, for all temperatures, delta G will always be less than 0, and this process will always be spontaneous.